This is where we are. We did decoders. We did multiplexers. We did the comparator. Comparator is an important one again because it's not only functionally important but also structurally important because it is iterative, means that you build a slice, repeat it. And we're going to be seeing another one exactly like that, which is the adder. And so let's do the adder, comparator, and now we are doing the adder. Okay. Once again, reminder where all these fit. They fit in the data path of an RT level circuit. Why do we do these? Because we want to add these little components in our bag so that when we are designing something, instead of designing using Carnot maps and all that, we reach our bag and say, oh, here is a comparator, let's use it. Here is an adder, let's use it. Here is a subtractor, let's use it, and so on. And this is where we are now, which is the adder. What does an adder do? Well, again, look, I have two 8-bit numbers, and I'm planning to build an adder, okay? I'm planning to build an adder, and therefore my first thought is, okay, this is an 8-bit A, an 8-bit B, and this is an adder, and produces an 8-bit sum, and then it also has a carry out, and maybe it even has a carry in, okay? Meaning that when you are adding, you start with a 0 or 1 carry in. If I go about it this way, then I have 9 plus 8, 17 inputs altogether, and then I have 9 outputs altogether. And obviously, we cannot do 17 variable Carnot maps. So let's say this is not going to be done, and let's look at it slice by slice. Okay, let's do it the way we do it in decimal. How do we do it in decimal? 393 plus 465. You add 3 and 5, 8, carry 0. You add 9 and 6 becomes 15 with the carry 0. That's 15, carry 1. You add the 3, 4, and a carry 1. That's 8. And then you have a carry 0 in the next position. And then the next position is 0. Okay? And what you did was you did slice by slice. Okay, so here, let's look at this slice here. This slice had a carry in, had a bit of A, had a bit of B. Now, here I'm looking at decimal numbers, but I'm really going to convert everything to bits, okay? A bit of A, a bit of B, and then that produces a bit of sum, but then it also produces a bit of carry out into the next bit. So let me show it like this. It creates a carry out into the next bit that will be considered as carry in. I destroyed all my numbers here. Okay. 8, 15, 1, and so on. All right. So that is carrying into the next bit, but then this is also producing a sum, which is the 5 down here. Okay, so I'm going to do exactly the same with the binary numbers. I start with This is my A, this is my B. I start from the rightmost bit and then assume that I have a 0 carry in. Okay, I have a 0 carry in, and therefore a 0 here, a 1 added together, that is a 0. See, the result of these three is a 0 here and a sum into the next position. No, the sum out here and then a carry into the next position. This and a carry into the next position, which is a 1. Okay, and then in the next column I have a 1 added with a 0, added with a 0. The result is a 1 and then a carry of 0. Next position, this one. So I don't get the numbers mixed up, let's highlight them. So this is this, and then this. Okay, so let's start the numbers. I have 110. The carry was 0, so I'm adding 3 bits. The result is 0. Carry into the next position is a 1. 100. The result is a 1. Carry into the next position is 0. Then again, I'm adding 3 things together. 0, 1, 1 becomes a 0. Carry into the next position is 1. 101 is a 0. Carry into the next position is 1. 110 is a 0. Carry into the next position is 1. 111 is a 1. Carry into the next position is a 1. 100 is a 1. Carry into the next position is a 0. 010 is a 0. Okay. 010 is a 1. Carry into the next position is a 0. Okay. All right. So instead of doing the adding by looking at two 8-bit numbers and a carry in, this is the carry in, this is the carry out. Instead of doing it this way, what I'm going to do is I'm going to look slice by slice. Look at each slice. See, when I do each slice, I'm really talking about a very simple combinational circuit. When I do each slice, I am adding a carry in, bit of A, bit of B. I'm only adding 3 things together. That's all there is to it, 3 bits together. Okay? And then what I'm doing is I have 2 outputs. One output is the sum, one output is the carry for the next position. So what I'm really doing is I need to build a circuit with 3 inputs, 2 outputs, and repeat this 3 input, 2 output circuit as many times as I want. Okay? And this becomes my 3 input, 2 output circuit. Okay? Look at everything that I had over here. Let's look at, for example, 1, 1, 1. The result is 1. The carry is 1. 1, 1, 1. The result is 1, and the carry is 1. 0, 0, 0. The A input, the B input, and the carry into this position is 0, 0. 0, 0, 1 is 0, 1. 0, 1, 0 is 0, 1. 0, 1, 1 is 1, 0. You are adding a 0, a 1, and a 1. Let me see if I can find the 0, 1, 1 situation here. Here. See? 0, 1, 1. The result is 0. And then the carry into the next position is 1. So 1, 0. So 1, 0. 1, 0, 0. Do I have 1, 0, 0 here? 1, 0, 0. Yes, I do. Is this one. okay, is 100 is this one. Okay, I'm getting a sum of 1, a carry of 0. 100. A sum of 1, a carry of 0 is this one here. 101. I'm not sure if I have it, but let's check. 101. Yeah, I do. 101 is this one over here. Okay, this one. 101. The carry, the sum is 0 and the carry is 1, and therefore is 10. So 101 is 10. Do I have 110? Oh, do I have 110? Yes, I do. Good thing is that I have everything that I have over here, so that's pretty good. So let's do 110. Is this one here? Okay, 110. The sum is 0, carry is 1. Is this one over here? Okay, so is 10. Is 10. And then I also showed you that I do have 111. 111, which is this one over here. 111 adds to 1 a carry of 1 into the next position. And okay, 111. The result is 1, and then carry into the next position is 1. So all I really need to do is build this circuit, this Carnot map, this 3-variable truth table. I turn it into Carnot map, one for the carry out and one for the sum. The carry out becomes a 1 here, a 1 here, a 1 here, a 1 here. The sum becomes 4 1s here. Okay, if you look at the I can map them, but if you look at the sum, you see diagonal pattern of 1s and 0s. This is usually exclusive OR. Okay, I look at the A and B and C, I see that the output S is 1 whenever the total number of 1s on the 3 inputs is odd. Therefore, the sum is nothing but exclusive OR of A, B, and carry in. Okay, in any order you want. You can XOR A and CI, and then the result would be, or whatever way you prefer to do it. All right, that is the odd circuit for the sum. Let's look down here. The carry out becomes 1 when the majority of inputs are 1. Okay, see, the majority of inputs A, B are 1. Here A, C are 1. Here A, C, or A and carry in are 1, the majority. And over here B and C are 1, the majority are 1. And therefore, this circuit can also be regarded as a majority circuit. Okay, carry out, A, B, carry in. Either that, or you can very easily write the Boolean expression AB or ACI or BCI. Okay, and this one is A exclusive OR with B, exclusive OR with CI. This is for the sum, this is for the carry. Okay, so what I do is I build a hardware that the sum of it is this and the carry out of it is this. Now, if you go back to the multiplexer, the first example I did for using multiplexers for the random logic, actually I had these two Carnot maps. Okay, so I can also implement these using Carnot maps. Go back and look at the multiplexers and you see that using two 4-to-1 multiplexers, I'm able to build the sum and the carry. So your choice of how you want to build this. It's up to you. You can build actually complex gates. You can use transistors, but all there is to it is one slice does it all. What I have here is the AB carry in and produces the sum. That is the odd circuit. Okay, odd circuit. Down here is the majority circuit, which is this. Okay, together, I put these together, a circuit with A, B, C, I, A, B, C, I. Majority gives me carry out. Odd circuit, odd, gives me the sum. Okay? And then repeat this. So let's look at this circuit again from a different point of view. This is that same circuit. I'm going to rearrange the gates slightly, and it becomes this. See, the SI is still the same thing. Okay. That is A with B XOR with C XOR. So this is the sum output, the sum for this particular bit. But then the carry out, instead of doing and or of the A, B, and CI, what I do is I do an ANDing here, okay, and then take the output of the XOR, that is XORing AI and BI. I take that and it with CI, and then only use one OR gate to, I'm sorry, I use a single OR gate with two inputs instead of an OR gate with three inputs, and then I drop one of my two input AND gates. This is a better circuit. This is a smaller circuit, and this is called a full adder. Okay. Remember that when I was doing my adding, I said that I start with a carry in of 0. Okay. If the carry in is always 0, I can always remove the carry in and not include it there at all. Look at this circuit here. If I remove the carry in, I'm going to do it using, let's say, red here. If I remove the carry in, this is 0, so this is 0, and therefore this OR gate is not needed. If I remove this, this XOR is not needed, and therefore this becomes my sum output. Okay, and therefore this part of the circuit is eliminated. The only part that remains is this part. If I don't want the carry, I can use a half adder instead of a full adder. Except the OR gate, this circuit is half of the original full adder. That's why it's called a half adder. Now, the good thing about a half adder is that it's not only for the rightmost bit. Actually, I don't recommend removing the carry in from the rightmost bit, because the carry in from the rightmost bit and the carry out from the leftmost bit, these are useful for cascading these adders. Okay, but then instead of using full adder, if you use half adder all the way through, then that creates an incrementer for you. Okay, a circuit that adds a 1 to your input. Remember, when I was doing two's complement conversion, when I was doing the absolute value circuit, when I complemented the whole number, I added a 1 to it using an incrementer. And this is the incrementer that can be built using half adders. There is no point in using an adder and putting only a 1 for the input of the circuit. So this is a full adder, this is a half adder, and then if I want to build the circuit that I was showing over here, if I want to build an 8-bit adder with carry in, let's say with carry in, what I do is I take 8 of these, or if this is a 4-bit adder. I take 4 of these and cascade them together like that. The carry out of one becomes the carry in of the other one. And each one has a C0, A0, B0, S0, and then the carry will be whatever bit number is. This is bit number 0, 1, 2, 3. Whatever bit number is plus 1. That means the carry out is C1. The carry out of bit number 1 is C2, and on and on. And the final carry is carry out, which is coming from bit 3, which is really C4. Okay, what if I use a half adder? Well, a half adder doesn't have a carry in, and therefore you only have two inputs. The very first one on the right hand side, you put a 1, and then you are adding a 1 to B0, and then you are carrying the outputs. Remember, notice that the half adder does have a carry out, which is this one here. This is the carry out for the half adder, and the half adder carry out becomes the input into the next one, and therefore this is a simple incrementer. Okay, there is no point in using a complete adder if your only task is incrementing. Okay, this incrementer has some good property. Look, if this one is 0, this incrementer doesn't increment. So it's really an incrementer with enable. If you put a 0, B passes through as is. No change. It puts some delay on it, but functionally no change. If you change 1 to 0, then B is added to 0. That means no change. So this becomes the enable for the incrementer. And so this is it. This is what I have for the adder. This is called ripple carry adder. The reason is, look, when I create a carry here, okay, the carry goes here. Then that carry goes into the carry of this, and then the carry of this is gone into this. This ripples into this and then creates this. This ripples into this and creates this. And then you have to wait for all the carries to go through completely before you can look at the output. Okay? For example, if, let me show you this number. Your input is let me think. Your input B is this, and your input A is this, for example. Okay, this is your A, this is your B. A changes to this. Okay. What happens is these two create a carry into this. These two create a carry into this. These two create a carry into this. These two create a carry, and this becomes the carry out. What it means is that for this particular input, you have to wait for the carry from the rightmost bit to ripple all the way to the left before you can count on the output. Okay, ripple carry adders are slow. What can we do? Well, we can do fast adders and carry locate adders, but not in this course. Just letting you know that, yes, in my bag, if I need fast adders, I can also put fast adders in the bag of RTL components that I'm using. This is how the carry ripples. Okay, let's do Verilog. Okay. One way of doing the Verilog would be to do the full adder just by itself. This is a 1-bit full adder. I am adding the A, B, and carry in, and then the result becomes a 2-bit number. The leftmost bit of the 2-bit number is carry out. The right bit is sum. Okay? So if I have 0, 1, 1 added together, that's number 2. Number 2 is 1, 0. And therefore, that's all there is to it. What I'm using here is curly bracket. Curly bracket groups what's inside it. Now I have a single bit carry out. I have a single bit sum. Grouping them together, that becomes a 2-bit vector. And therefore, this is a full adder. I can also write the full adder using its Boolean expression. Sum equal A ended with B, A exclusive or B exclusive or C in, which is what I first proposed, which is this circuit over here. Okay. For the carry out, remember A and B, A and C in, and B and C in, or together, that's carry out. And therefore, either one of these descriptions is good. How about the 8-bit adder? I can either take a single full adder, repeat it 8 times as I wish, or any number of times as I wish, to build a larger adder, or I can write an 8-bit adder. An 8-bit adder is A and B 8 bits carry in, and then sum is 7:0, and then I have the carry out, and then I use the same exact description that I used up here, except that down here my capital A and my capital B are 8-bit vectors that I'm adding. On the left, this is a 1-bit vector, this is an 8-bit vector. The 8-bit vector and the 1-bit vector concatenated together form a 9-bit vector, and therefore the final carry will be captured by the leftmost bit being carried out, and therefore this is a good 8-bit adder. No need to instantiate 8 full adders. What if I need extra things with my adder? Like what? Like, for example, see, this is giving me carry out. What if I want a 0 flag, meaning that the output Z flag becomes 1 when the result of the adding is 0? What if I want a negative flag? What is that? The negative flag becomes 1 when the result of the add is a negative number. Remember that these adders are adder subtractors, meaning that if you have two 2's complement numbers, they're going to perform fine. If you have a positive 2's complement and a negative 2's complement, this is going to work perfectly. Okay, so it is really a 2's complement adder. And therefore, the result of the 2's complement may be negative. Also remember, when we did the adder, when we introduced binary adding, we said something like this. What if I have two numbers that I'm adding? This is a positive number. This is a positive number. Okay, I'm adding this. This is a 1, this is a 1, this is a 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, and then a 1 here. I'm adding two positive numbers. I'm getting a negative number. This is bad. This is overflow. Okay, what if I want my adder also to have an overflow flag? What I do is I do something like this. I add, in addition to the carry out, I also put the 0 flag, the negative flag, the overflow flag, and then just make assign statements for each one of these. Line 25 says negative flag is 1 when S7, that means the sign bit of S is 1. 26, the 0 flag is 1 when the NOR reduction. This is called a NOR reduction. Okay, a NOR reduction means this. you have the OR symbol on the left-hand side of S. Okay, see, we are used to doing something like, for example, A OR with B, right? But then if you don't have A or B and you only have a vertical bar and an operand, this is called a reduction operator. What a reduction operator does, instead of bitwise ORing that this one is, what it does is it takes all the bits of S and ORs them together. Okay, so this is no reduction, meaning that first all bits of S are ORed together. That means this. Okay, and therefore if all of them are 0, this is going to be 0. If all of them are 0, you put a bubble here, which is that NOR action. And therefore, this is the NOR reduction of S, which makes the Z flag. Okay? And let me highlight this. This is NOR reduction. Okay? And that's a different NORing than this, or that's a different ORing than this ORing. See, this ORing, it has two operands on the two sides of it. And therefore, the two are being ORed together. If the vectors are, if what I'm ORing are vectors, then it will be bitwise ORing. But in this case, for the familiar overflow flag, what I'm ORing is A7, sign bit of A, sign bit of B, and then sign bit of the result, complement of it, and complement of A. So this is the logic I'm doing. Remember this, we did this. This is A7, this is B7, this is S7. Okay, and then this, this, and this, ORed together. Okay, and that's my V flag. This is my Z flag, and the negative flag is nothing but just taking the a wire off S7. How about the incrementer? The incrementer, I can write the description of the half adders and instantiate 8 of them, or even easier, I can take A and then add a 1 to it, and then that becomes carry out an S. Okay, once again, carry out is concatenated to the left of S, so that the 9th bit result of A plus 1 is captured by carry out. So these are various forms of Verilog descriptions for the single bit, for the incrementer, for the adder. All right. What if I want to have an adder that sometimes adds A and B, sometimes subtracts A and B? Okay, look down here. A minus B, these are 2's complement numbers. These are 2's complement adders. Okay, A minus B is A plus minus B. Okay, what it means is instead of subtracting, and that's the whole idea behind 2's complement numbers. Remember, when we talked about 2's complement numbers, we said that I like a system in which adding and subtracting can be done in the same way. Okay? And then we said that instead of adding, instead of doing A minus B, I'm going to do A plus B or a plus minus b, and then minus b is in 2's complement. So here what I have, a plus minus b. Minus b, how do I calculate this? This is 2's complement. How do we calculate 2's complement? We calculate 2's complement by complementing all the bits of it and adding a 1 to it. And therefore minus b is b, meaning all the bits of b are complemented, and adding a 1 to it. Therefore, look at the left-hand side. Don't look at the right-hand side yet. If I want to subtract a minus b, perform a minus b, for example, which is this. Okay. I put a here, and then I complement b. Okay. That this. This is complementing b. But that's not enough, because 2's complement of b is complementing and adding a 1 to it. Remember I said I don't recommend removing the carry in. Now that I need a 1 to be added to the b complement, I can just bring in this 1 and put it in the carry in, which otherwise would be useless. Which otherwise I would be putting a 0 in it. See? Here, I have a 0 here. Why? Because I don't need it. Since I don't need the carry in, I said, leave it there anyway. If you want to cascade this, if you want to have another 4-bit to the left of this, you can do that. Or, if you don't want it, just put a 0. Don't put a half adder. Put a full adder. If you don't want the carry in, just put a 0. But then if you want to turn it into a subtractor, put a 1 here. This becomes a subtractor. Okay? So that's a subtractor on the left. What if I want a circuit that sometime I have to decide whether I want a subtractor or an adder? Okay? The circuit I design is one that sometimes it inverts, sometimes it doesn't invert. And also this one, sometimes it puts that 1 in there, sometimes it puts a 0 in there. If I want to add, I will let b's to go through untouched, and I put a 0 here. So let's do this. Let's do this. If I want to add, I'm going to be using this color. If I want to add, I want the b's to go through and put a 0 here. Okay, that's for add. If I want to subtract, I want b's to go through the inverter, get inverted, and then I put a 1 here as I'm showing. But then there is a signal that becomes 0 when I'm adding and becomes 1 when I'm subtracting. That signal, I call it add bar subtract, or A bar S. A bar S. That means it's 0 when I'm adding, and it's a 1 if I'm subtracting. Remember the good old XOR gates. I said that XORs are comparators because they compare if the two inputs are equal, the output becomes 0. Okay? And XNOR is the opposite. So it is a comparator. It is a parity circuit, meaning that if the number of ones on the XOR is odd, the output becomes 1. Okay, that's another one. I'm also claiming that XOR is a controlled inverter. It's a controlled inverter. Look, A, B, XOR of A and B. 0, 0, 0, 1, 1, 0, 1, 1. Okay? In the situation that A is 0, yellow, A is 0. Let's say A is the control. Okay? The output is 0, 1. In the situation that A is 1, okay, in the situations that A is 1, which are these two cases, the output is the complement of B. Okay, the output is the complement of B. So this is a 1, this is a 0. So I can say this is an XOR. A is the inverter control and B is the input. If A is 0, B goes through. If A is 1, complement of B goes through. Isn't this something that I wanted for the inverters in the left side adder anyway? So what I'm going to do is, instead of having the inverters, I'm going to put XOR gates. XOR gates, they have the add sub control, and therefore they're going to either complement the B, or either complement the B or let B go through. Also, if I'm subtracting, remember here that I was showing that I also need to add a 1 to it, and therefore I bring in that add sub signal, bring that into the carry in, and therefore that adds the 1 if I'm subtracting. Perhaps this was not a good choice of symbols. Let's use, for example, X and Y, and this is the XOR of it. Okay, so that the A and B doesn't get confused with the okay, so this is X and Y, that X controls whether Y is going to be complemented or not. Okay, which is exactly the way I'm using the XOR for complementing or not complementing B. What I've done here is not only the adder, I also showed you an adder subtractor. This is good for now, and let's go on to the next item, next part, and that is an ALU. ALU says this. Not only I add or subtract, I do a lot of other things. So let's next talk about